In the last chapter, we completed the backpropagation, and that was for calculating how the learnables have to change in the different layers based on the feedback from the loss function and the gradient of the predicted, which we calculate from the predicted probabilities compared to the actual assignments of the different classes. And now we want to minimize the loss and maximize the accuracy in an automated fashion. And therefore, we want to build a new class which will contain an optimizer. So this chapter is about optimization. And before we start with the code and the theory behind it, I want us to go back to our network. So we have our code where we have our dense layer, the activation of the ReLU, the softmax activation. Then we have the loss function, and we have a class that where we can calculate the cross entropy. And then we have a class where we call both the softmax layer and the class for calculating the cross entropy, so that we can calculate both and then calculate the gradient of the calculated probabilities with respect to the actual classification of our data points. So our module is now relatively big and relatively sophisticated. And also we have our function or our script where we can test our module. Before we continue, I would just recommend to change this value here. So remember, that's the number of neurons in the first layer. That's been 5 before, and we should change it to 64 or a number comparable to that. Then we call all the different classes. Then we set up the forward part of our network, and then we feed back the discrepancy between the predictions and the actual class vector into the backward part, and it just propagates back to the first layer. And what I started already in the last section, and what you can see here already, is that I prepared something. So in principle, now we have the feedback from the backpropagation, and you can calculate change of the weights for both layers. And according to gradient descent, so that's what we derived earlier, we have to subtract the change multiplied with a constant, which is going to be the learning rate. So it tells us how large these steps are, so how fast we want to make progress in this particular direction. And the same, of course, is true for the biases. So in principle, I can run this code now many times. So changing the biases in the weights, then starting the forward part again, then we should have an improved accuracy and an improved loss. We still would have a discrepancy. So we will move on with the backward parts with the backpropagation. And again, it would imply the changes of the weights and the biases. And again, we would feed it in the forward part. So that's something we would do now for many iterations, and we can actually test this already. So let's say, for example, A is our learning rate, and let's start with a value 0.1. So that's really just a guess, so we don't really know. And we want to run this in a loop. So therefore, we shift the whole thing to the right. And then we want to have a certain number of iterations, let's say 10,000, which is okay because it's going to be very fast. And then we say for E in range N, and E is called, so this iteration is actually called an epoch. So an epoch is essentially running the entire data set through the entire network, including the backpropagation, just once. And this is called an epoch. Later, when we create our CNN, when we work with images, we will see that the entire data set is too large in order to load it once into the entire network. So we will divide the data set into smaller parts, so-called mini batches, and then call these mini batches, run them over the network a few times and then call another mini batch randomly and do the same thing. But here we can feed in the entire data set immediately because it's small enough. So we want to run this now, and we also want to check the loss and the accuracy. So let's start with the accuracy. And we want to check whether the accuracy is really increasing. So we can actually just run this all together. So let me just do that. And you see the accuracy goes up. So we start with 1/3 roughly, and it goes up to 0.7, even a bit higher. And here we are. So that's the accuracy, and you see it works. It's not perfect. It's not 0.9 something. So if you want to use your network for commercial uses, so usually 0.98 is acceptable, so to say. So it's not perfect, but we see that it works in principle. So our network is able to learn. And by the way, if you run such a code which contains already lots of lines for the first time, even though we just checked all the things in between, you usually get an error message, and then you have to find the typo and have to fix it. If you don't want to spend too much time on that, of course, I put every step that we took on my GitHub repository, so you can just download the code and just run the code if you made a typo in between. So don't worry too much about it. So then you can run the code, and then you will end up with roughly the same result, not exactly, because remember the weights and the biases initially are set randomly. So there is some certain randomness in the process. So you should end up with a value which is close to 0.7, maybe 0.68 or so, maybe even a bit higher than but not necessarily exactly the same thing. So then we saw lots of progress, so it works, and our learning rate was 0.1. What we could see here, and it's very typical for a relatively large learning rate, like in our case, the network seems to oscillate. So it jumps from 0.71 to 0.725 and so on. But it doesn't improve. So somehow it just oscillates. And the reason is that our step size is too large. So just imagine you walk along the loss function and there's a minimum, and step size is so large that you just jump from one edge to the other one and always jump over the minimum. So first you have a negative gradient, then your weights go to the right, then you have a positive gradient, they go to the left. They don't make any progress because our value here, our step size is too large. So one idea could be to reduce the step size, and let's run it again. And of course, we have to call the network, the instances again. Why? Because we changed the weights. So we want to run our test in an unbiased fashion, of course. So we'll just call the instances again. And this time we have a smaller learning rate, and let's see what we get now. And step size is 10 times smaller. It makes progress, but didn't get that far. And maybe the step size is too small. And that's already one thing we have to fix. So if the step size is large, it makes lots of progress at the beginning, but then you probably do not hit the actual minimum. So it tends to oscillate. If the step size is too small, two things can happen. So either it just takes longer because the step size is smaller to reach a certain value, or you can get stuck in a local minimum. For a larger learning rate, you probably might have jumped over it, but if the learning rate is smaller, so you perform smaller steps in the loss function landscape, and then you might get trapped somewhere in a local minimum. That's actually what might have happened here, because after a while, it didn't change at all. And therefore, we have to do two things. So first of all, an idea would be to start with a large learning rate and then decrease this learning rate step by step during the different epochs. And another thing is to take the vicinity of our current data point in the loss function space into account. So what is the actual shape of the gradient in order to kind of prevent that our network gets stuck in local minimum, so that we somehow figure out, okay, that's only local minimum and the global one is probably still somewhere else. And we're going to do this then later as well. And in principle, you could do this already now in our code, but it's very inconvenient. We want to do this in an automated way, and therefore it makes more sense to create a new class, and this is going to be the optimizer. So that's the idea now. We create the optimizer, and let us therefore just go back to our slides and take a look at the theoretical background. So what was the idea? So the idea was gradient descent. So we have a loss function, or it's also sometimes called a cost function. So that could be either the accuracy or the cross entropy. And that depends on the parameter raw. So raw could be the weights, could be the biases, could be any other learnable. And the idea is still the same. So we have a value at some iteration I, and then we have a value at iteration I plus 1. And ideally, we would reduce the cost function or the cross entropy, like in our case, the loss. And we ideally approach the hopefully global minimum. And we do this by calculating the gradient, and the gradient approximately is just the difference between these different two values of the cost function divided by the difference of the parameter the cost function depends on. So again, it could be the weight delta W. And then based on this, we derived our algorithm, just gradient descent. And the step size is determined by the learning rate alpha. Well, and that's the first thing that we do. So, but we should take into account that we, in principle, get stuck in a local minimum, for example, here. And later, we also want to implement something, so-called momentum, that helps to reduce the probability that something like that can happen. So the learning rate is a so-called hyperparameter we have to give. And you saw already that the performance of the network strongly depends on the learning rate, on this hyperparameter. Later, if you work with neural networks, there are many other hyperparameters, and you kind of try to scan the hyperparameter space to find the optimum. So you can really do this by just scanning the parameter space, which is computationally very costly and not very efficient. But there are other algorithms that look for kind of the sensitivity, so how the performance of the neural network depends on the hyperparameter, how you change it, and then you, kind of move along a so-called hyperband. That's also how this algorithm is called. So if you just want to Google that, just Google hyperband. And then we have the learning rate. We need to update the weights and the biases according to the derivatives. So that's what we did already manually. And we want to do this in a optimizer, and we want to call this optimizer SGD, which stands for stochastic gradient descent. And all these optimization algorithms are more or less different versions of gradient descent. So you can use an adaptive step size. You can change many other things as well. But at the end, it's still the same idea. It's gradient descent. So that's the idea now. And we set up a new class. And also here, it makes sense to start with an init where we set the learning rate. And we can actually start with our default learning rate 0.1 that we have tried already, because then we reach an acceptable result. Let's say it like this. And then we want to set up a new method that we just call update parameters, where we just perform exactly what I showed earlier manually, so that we just look into the layer, look into the weights and the biases, and just update them accordingly. So, and then we just will add this to our routine and see whether it works. So therefore, let's go back to our code and let's implement our optimizer. Also for here, I would recommend to open a new chapter And this really follows the chapters or the folders I have in my GitHub repository. So that's easy for you to compare your codes to the codes here, and it's ordered in the chapters accordingly. So we just call it optimizer. And therefore, we just move to this particular folder, optimizer, and we also want to save it in the optimizer. And we're going to do the same with the A and M. All right. So then we just set up the optimizer. So we just say class optimizer underscore SGD. And we start with the init. And we set as a first input parameter the learning rate. And let's set 0.1 as a default value because it turned out that we have already an acceptable result of that. So then we also want to save the learning rate. You will see later why. And then we add a new method, and we want to call it update parameters. Where we feed in the layer and where we essentially perform this here. So we can just copy and paste that. And of course, that's a variable name. So we just name it layer. And later, when we have the convolutional neural network, we will see that we don't have only the weights and the biases of the dense layer. We will have so-called convolution layers, and then we also will have the equivalent of weights and biases. So we also can use and that's the whole idea, we can also use the same optimizer for all the other different networks we are going to build. And that's the reason why we want to keep it very generic. So we call it layer. And then we add the learning rate. Let me just change this a bit. So let me just say it is plus, and then multiply it with a negative learning rate. And you will see later that there is some reason for that. I mean, it's mathematically, of course, equivalent, but it's more about having a code where it's easy to understand what it actually does. So we just take the learning rate and multiply it with the learning rate. And that's it. So that's everything we need to do. So of course that's then redundant. And now we have all the different layers. All right, so here we are. And then we can test it in our network. So let me just compile it again. And we can test it in our network. So what is the idea now? So we import our network, of course. All right. And then it should recognize the optimizer. And here it is. And let's start with the default learning rate. So we just say optimizer equals our optimizer here. Then we don't need that anymore. And then we can just modify the weights by using our optimizer. So how are we going to do that? So if we just call the optimizer, all right, then we have the method update parameters. So we have the learning rate saved, but we also have the method update parameters. And remember, this method looks into the layer and updates the parameters accordingly. So we can delete this part here. And then we just say update parameters, and the input is the layer. So that's what you can also see here. The autocomplete says, and the first layer is the dense layer. So the first dense layer, and then the second one. By the way, the order doesn't matter because it's within the same epoch. All right, let me just test run this again. So let me just remove this part here. All right, and then let's test run it. And we should end up with roughly the same result as we had before, so something close to 0.7. And you see, it's kind of oscillating again. Not that bad as before. We even have a slightly better accuracy at the end, but it's just pure coincidence. Well, that's the stochasticity and the whole process. All right. What I also did in the book is that they add print output. We also want to do that. So if not epoch, so the epoch E, let's call it then also epoch. So if not epoch, and you divide it by 100, and if it doesn't have a rest, then we can say print. So just showing you what the idea of that is. So for example, if you have, I don't know, 120 and say 100, then there's a rest, right? Which is the 20, and if you do that, there's no. So that means if we say if not epoch to send 100, it means every time I have 100, 200, 300, and so it's gonna print out the results. And we wanna use the f string, and we want to show the epoch. Just the name epoch. Then we also want to print. We want to leave some space that it looks nice. Then we want to also print the accuracy. With 3 floats, so we want to print accuracy with 3 figures after the dot, and then we also want to add one more. So we also want to print the loss. So okay, so it's a float. That's what the F is standing for, and it's a 3 means 3 figures after the digit. All right, so that actually should work. So let's run it again. I want to just remove all the plots, and let's run it again. And now it plots the loss and the accuracy. You saw, I forgot one space here. But you see we have the different epochs, the accuracy goes up and the loss goes down. Let me just run it again. So that looks a lot nicer. But we saw earlier that the network also might lead to oscillation. And of course, we will see that in the numbers anyway. So that's what we did earlier. So we saw it in the numbers. But it's always nicer to have a plot. So we also kind of want to monitor how the accuracy and the loss changes over the epochs. So we also want to just include another matrix, and I would just want to call it monitor, because we want to monitor the result. We just start with zeros, and it will have the size or the shape n times 2, because we want to monitor the loss, the accuracy over the epochs. So we just go there in our loop and then just say, okay, monitor, and for the epoch in the first column, we want to have the accuracy we want to give it in percent, so times 100. And then we also want to monitor loss. And we also want to plot this, so just put this in one plot with different subplots. I think we have to, yeah, the matplotlib already. So be careful, there's subplot and subplots, and we need subplots. We want to have 2 rows and 1 column, so 2 plots underneath each other, and then we want to have different axes. The first axis is just a normal plot where we want to show the monitor. We can use np arrange n, and we want to plot the accuracy in all rows, column 0, and we also want to label this, of course. And we want to plot the loss as well. And we also want to set the X label. Which is the number of epochs. All right, so let us again just run it. So let's call the network again, set up the network again, because of the weights are changed already. And then you see again how the accuracy improves, how the loss improves, and we now also get the plot. And you see how the loss drops dramatically And you also see how the accuracy goes up. And you see the curve is kind of getting flatter. So if we would increase the number of epochs, we would probably not increase the accuracy too much. And that's one thing we can actually see already. And if you run the code with the same parameters, so remember, we have 64 neurons now, you should get roughly the same curve as well. And we can also play a bit with the neurons. So for example, if we have fewer neurons, let's say we have over 5 neurons. Let me just remove that and let me just run it all again. It's first of all faster because, yeah, you have fewer parameters and you see, well, the problem is that the number of parameters, so which is determined by the number of neurons, of course, is probably not sufficient in order to account for the complexity of the data set. And that's what you can see here. Just think about fit where you have not enough data for, or let's say it like this. So let's say you have a fit and you have fewer parameters for the fit you actually would need in order to describe complexity of the problem. So we need to increase the number. So we had 64. Let's try 128, or let's try 200. I don't know, 250 or something. And let's see whether we can increase the accuracy. And what you see here, it's of course slower because again, we have more parameters now. We have a larger matrix, and that makes the code slow. Since we have matrix multiplication, so just normal algebra, that is actually a possibility. There's a possibility to parallelize this easily because these matrix operations are independent from each other, right? If you multiply a vector with the first row and then with the second row and with the third row, these operations are independent from each other. So we can actually speed up this process easily by parallelizing the process. So that's one of the strengths, actually. If you have a neural network like this, you can run all these processes or most of the processes in parallel. And what you can see already now that the accuracy, in fact, actually improves. So it goes up to 0.83. And we have increased the number of neurons by a factor of 4 point something. And you see that matters already. It makes the code slower, but again, you can run it in parallel. So that's not a big deal. And then you have a better result. So therefore, we're actually done with what we wanted to do. So we have created a fully functional neural network from scratch. And then it's time for saying congratulations. If that was your first neural network you have created, then congratulations and thanks a lot that you have followed this lecture so far. I really appreciate it. But we're not at the very end because we can still improve our process of learning. So for the network and also of training. So how do we train the network? And then of course we want to also apply the network. So we want to see how does it actually predict the class of our data points depending on how much information it got earlier. And this will be the last chapter of the first section of the core, where we will improve the training process and where I want to explain more about the learning, so how a network actually learns.